Hi everyone, welcome to this class 18A, where we say goodbye to all the math of the previous classes and hello to combustion engines and the corresponding thermodynamic cycles. And like the previous classes, this one is provided to you by Wout and by myself, Jeroen. And before we go on, I'd like to spend a few words on the pictures that you see here. You see a picture to the left of what's called a Langer Heinrich. It's a German floating crane that was built in 1915, and you can take it out onto the sea and you can lift submarines out of the water with it if you want. Um, it was originally built with a steam engine, but in the 1950s it got refurbished with four diesel engines that power electrical generators. And you see a picture to the right of such a diesel engine, which is a big device that produces more than 400 horsepower. Nowadays, an average German turbo diesel Audi or Volkswagen can easily have 100 or 200 horsepower in a much smaller device. But then again, we're 70 years later. Okay, so much for Langer Heinrich. So I just mentioned all the math of the previous classes. In the previous classes, 15 through 17, we learned about the different thermodynamic energies, about their total differentials, the partial derivatives that are involved. We learned about the Maxwell relations that can be very useful to convert partial derivatives that contain, for example, the entropy, which is always a bit problematic because you cannot measure it. You can convert these partial derivative differentials to expressions that contain properties that are measurable. And well, we also learned a little math relations that allow us to um, uh, reshape partial derivatives, all these rules that we actually use to derive these Maxwell relations. And in the final class, we even learned sort of a general recipe that we can use to express any partial derivative into a useful form in terms of quantities that can be measured or that are otherwise known. So, for example, partial derivatives that are known or can be measured are things like this dv dt, which is related to the thermal expansion coefficient beta. There's things like compressibility. Well, we have seen and discussed all these relationships at length, and I'm just showing them again just to remind you that we actually did all this stuff. And in the end, we also managed to express the thermodynamic energies, for example, the internal energy, in terms of all these measurable or known coefficients. And that can make life very useful, very pleasant. Let me put it that way. You can also do this for the enthalpy, for example, and you can even convert properties like entropy into expressions that again contain only measurable quantities. Very nice, because it allows you to understand where these tables and these diagrams come from. These are actually the expressions that are used to produce these tables and diagrams. And just maybe as a brief exercise, uh, let's take a look at this expression for the entropy here. Um, you see this specific prefactor in front of the dp differential. Well, we know that has to be equal to the partial derivative ds dp for constant t. Um, but we also, I mean, if we look at this expression here, v times beta, if we look at beta, well, if we multiply that with v, or minus v, then we end up with minus dv dt at constant p. Hey, and this was indeed one of the Maxwell relations. Well, what I've done here is basically uh, uh, do the derivation in the reverse direction, just as a reminder of how these things work. Now, about the coming two classes, they build on what we studied already during block 4, where we learned about thermodynamic systems that we can use to produce power or generate work or to transfer heat. Some of these were discussed in class 6. And we have seen vapor power cycles like the Rankine cycle, which produce power using a working fluid that actually changes phase from fluid to gas, for example, during the cycle. That was discussed in 7 and 8. We have seen gas turbine cycles like the Brayton cycle, where the working fluid is in the gas phase throughout the entire cycle. That was in 10 and 11. And we've also seen refrigeration cycles, where power is used to transfer heat from a cold zone to a hot zone. That was in class 13. Now in 18A and 18B, we will study gas cycles pertaining to what is called external combustion and internal combustion engines. Examples of such engines are the Stirling cycle, that actually uses external combustion, and the Otto and diesel cycles that use internal combustion. And all these engines, they are piston cylinder devices, which are also called reciprocating engines. Now, gas power cycles, they use gas as a working fluid. That makes sense. And you can have closed cycles where the working fluid is contained in a sealed container. So it's not exchanged or dumped into the environment. This is a type of engine where you typically use external combustion, and combustion is written between quotes here because it can be literally combustion, but it can also be heat provided by a nuclear source or geothermal source or solar energy. In the picture, you see a sort of a parabolic mirror that concentrates solar energy, light, and focuses it into a Stirling engine. And on the next slides, we will actually look at Stirling engines. So this is not combustion. This is literally solar energy in its purest form. In such closed cycle systems, people like to use helium as a working fluid because helium atoms are light, and for that reason they move very fast at a certain temperature. And if they move fast, you can have efficient heat transfer. You can have the same thing with hydrogen, which is even faster because it's even lighter than helium. But hydrogen can be tricky. It's explosive if you mix it with oxygen, whereas helium is completely inert, so that's safe. And helium also has a relatively low heat capacity, which means that if you add heat to it with the purpose of making the gas expand to generate work, then the heat that you add is really efficiently converted and not converted into internal energy of, for example, vibrating molecules or what have you. So I already mentioned the Stirling engine as an example, so let's take a look at that. Actually, let me take that back because first I want to discuss open gas cycles where the working fluid is exchanged with the environment. So it's an open system. Engines have an intake and an exhaust. Clearly, we are talking about also the kind of engines that you will find in cars, traditional cars with combustion engines. The combustion takes place internally. And that's why they're called internal combustion cycles. And the working fluid is a mixture. It's a mixture of air or some oxygen containing gas combined with fuel. And then after the combustion, the fuel will have been gamically transformed into combustion products along with the remaining air. And examples of open gas power cycles are the Otto cycle, the diesel cycle, but also the Brayton gas turbine cycles. Now, there is something that's called the air standard cycle. Um, it's a tool to simplify real gas cycles. So it's an approximation, and it's useful to understand trends or comparing different scenarios in a qualitative way. But it's not so good for a detailed quantitative analysis. And the assumptions that are being made in the air standard cycle approach are that air behaves like an ideal gas. Um, the working fluid is actually dry air without any other contents. So we ignore that there may be fuel or combustion products. So that's a simplification. And we replace the internal combustion with some sort of heat transfer mechanism. And sometimes also the exhaust and intake processes are modeled as heat transfer mechanisms too. Apart from these simplifications, other assumptions are made in the air standard cycle. And that is that the specific heats of the gases are constant. And we take their values of the values at 25 degrees C, which is called the cold ideal air standard cycle. And then now let's talk about the Stirling cycle. It's actually the oldest gas cycle that exists. It was developed by Robert Stirling, a Scottish engineer. Um, it's a closed cycle, so it requires external heating or external combustion. And the cycle, the thermodynamic cycle, is depicted here to the right. Uh, it's a PV diagram, and the cycle consists of two isochoric processes from 4 to 1, for example, and from 2 to 3, and two isothermal processes that take place along an isothermal curve or an isotherm. There's also a thing involved that's called the regenerator. It's a way to recycle heat. We will see how that works in detail on the next slide. And the Stirling cycle, well, in principle, it allows you to achieve high efficiency, approaching the Carnot efficiency. And in theory, you can even achieve the Carnot efficiency, which is 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. We've seen that formula before. But achieving such high efficiencies with a practical Stirling engine is, well, turns out to be difficult. And Stirling engines that make use of this Stirling cycle, they come in different forms. They can have either one cylinder or two cylinders. We will see at least one of them in the coming slides. So let's take a look at the principle of operation of the Stirling engine or Stirling cycle. So we saw this PV diagram before. This is the same cycle, but now expressed in the TS diagram. And here you see that this section and this section are clearly isotherms. And actually, well, let's take a look at the transition from state 1 to state 2. So here is a depiction of a Stirling engine that is a cylinder containing two pistons. The pistons can move. Actually, they're connected to the same flywheel or crankshaft, if you will, but they don't move always in the same direction or at the same speed, as we will see. This Stirling engine has a body of gas that is going to be shuffled between a hot zone and a cold zone. So everywhere in this graph here is the hot zone, and this is a cold zone. And there's something that's called the regenerator. That's this pink thing here. And what is a regenerator? Well, it's, for example, a wire mesh, a copper wire mesh that can absorb heat. If there's hot gas flowing through the wire mesh, the mesh will heat up and it will keep it. You can consider it isolated from the environment, so it will heat up. Then the gas will flow to this side where it will cool down. And when it is pushed back through the regenerator, this wire mesh is still hot and it will heat up the gas again before it goes back to the hot zone. Let's do this step by step. So the first step is this isothermal expansion, going from state 1 to state 2. So what does that step mean in the engine? Well, we have some gas here. This is the hot zone. So the gas is heated up. Actually, heat is added to the gas, but the gas never heats up. Instead, the gas starts to expand. So the heat is converted to a higher pressure, and the higher pressure will actually push out this piston. So it will actually start doing work. Now, now that we have the heat into our gas, it's time for the next step. That's isochoric heat rejection. So we want to take the hot gas to the cold zone, and we do this in an isochoric way. And what does that mean? Well, we have this volume here in between this piston and this piston, and the two pistons will move at the same speed towards the right, like is indicated in this picture here. So the volume doesn't change, but this gas is moved from the hot zone to the cold zone, and in the meantime it is pushed through this regenerator, this copper wire mesh, for example. So that heats up, so that will cool down the gas already a bit, and then the gas is here, and then it will cool down even more. That's the next stage where we go from 3 to 4, or here it's through this process, it's again isothermal. So heat is now given away to the environment, to the cold heat sink, and while heat is being given away to the environment, the temperature is actually not allowed to drop, because this piston will compress the gas. So it will stay at the same temperature. The volume here will decrease. And that's when we have reached the end of the cycle, and we can start by going back to state 1. That's again isochoric heat addition. So we have the state here, state 4, with the two pistons separated by a certain amount. All the gas is at the low temperature at the cold zone. And now the two pistons will move at the same speed to the right. So the volume stays the same. And now the cold gas is being pushed through the regenerator, and the regenerator will give back its heat to the gas. And if everything works perfectly, then the amount of heat that was added here in this step, these two steps, is given back to the gas. So this regenerator uh, absorbs and gives back an amount of heat, QR. And as a result, actually, because you preheat the cold gas before it gets to the hot zone, you don't need to do as much heating as you would need to do without regenerator. So you need actually less heat going in. Q in is actually smaller. It's smaller by this amount here, QR. The same is true also for what happens here on the other side in the cold zone, because when you push the hot gas to the cold zone, well, by the time it gets there, it will have already given away some of its heat to the regenerator. So also the outgoing heat is less than without generator, and it's reduced by the same amount. And well, let's take a closer look at how to analyze a Stirling cycle, and also what the effect is of the regenerator. When we analyze a Stirling cycle, well, the simplest thing we can do is assume that it's an ideal gas that we're dealing with. This regeneration, like we just saw, it reduces the heat that goes in, and it also reduces the heat that goes out by the same amount, QR. Now, if you look at the expression for the efficiency of the cycle, that's 1 minus Q out divided by Q in. but Q out was reduced by QR and Q in as well. And I can rewrite this expression in the following form. I have this fraction here, and QR no longer shows up in the numerator, but it does show up in the denominator. And since QR is bigger than 0, it's implied that this fraction becomes bigger because of QR. And this entire fraction is equal to the efficiency. So this regenerator, this bit of heat QR that it recycles, that actually improves the efficiency of the Stirling cycle. We can also take a look at these all these different segments in the cycle again, and for example, going from 1 to 2. Well, there's a thermodynamic property that's constant here. That's the temperature in this case. And the heat that goes in, that's ideally all converted to useful work if everything is perfectly reversible. So the heat goes in is the work that we will get out. And the work, of course, has to do with the fact that we have a change in volume at a certain pressure. Now, in this part of the cycle, from 2 to 3, this is the isochoric part, so there is no change in volume. Hey, so there can't be no work done. And so W is 0, and there is some heat involved by the regenerator. This is actually this QR. Well, we can follow a similar line of reasoning in the next steps of the cycle, where we again have an isothermal process, where we actually have to put in some work to make it work, and so on. So this completes this slide. Now, on the previous slides, we saw a lot of piston movement inside cylinders. I'd like to bring a couple of definitions to your attention. The diameter of a cylinder, that's also called the bore. Then the piston inside the cylinder can have a lowest point. So when this surface here reaches this line, that's the lowest it will get. That's called the bottom dead center. And when it moves up, when it reaches the highest point, that's called the top dead center. And the distance between them, that's what's called the stroke. And there's another concept that's called the compression ratio. That's the ratio of the maximum volume inside the cylinder during a cycle to the minimum volume inside the cylinder during a cycle. Now, in the following movie, Wout will tell you about a different kind of reciprocating engine, the Otto engine and the corresponding Otto cycle.
Hi everybody, welcome to a new video about thermodynamics. In this video we'll discuss the Otto cycle, and the Otto cycle is a theoretical cycle on which the spark ignition cycle, the spark ignition principle is based. And when we're talking about the spark ignition cycle, you can think about a gasoline engine. Now actually I brought a model of this, or well, actually it's not a model, it's a real engine. It's the one belonging to a chainsaw, and I'm going to use this to explain a little more about the working principles of the Otto cycle. In this video I'm going to discuss the layout of an Otto cycle. After that we're going to discuss the real spark ignition cycle versus the ideal spark ignition cycle, and that's the Otto cycle. And after that we're going to calculate the work of an Otto cycle, so of an ideal cycle. And having discussed that, we're going to dive into the differences between the real Otto cycle and the ideal cycle. The Otto cycle is the idealization actually it's a spark ignition cycle. So the Otto cycle is the idealization of an internal combustion cycle, and in this, when concerning the Otto cycle, we're talking specifically about the spark ignition cycle. We have the diesel cycle as well, which has slightly different principles. That won't be discussed by me. Jeroen will discuss this later in his lecture. When discussing the Otto cycle, there are two different types of Otto cycle. We've got the 4-stroke Otto cycle, 4-stroke, and we have the 2-stroke Otto cycle. And the working principles of the 4-stroke and 2-stroke cycle are a little different, not very much. I won't discuss them in very deep detail, just give you an overview. The engine I've got here is actually a 2-stroke engine. Small engines are usually 2-stroke engines. So, first let's discuss the layout of such a cycle. I'm going to start with the 4-stroke engine. The first things we need to discuss is the most important item is probably the piston that's over here. It's a cylindrical unit and it moves up and down, and that's actually the heart of the engine. So this is the piston, and the piston moves within the cylinder. And the piston drives a crankshaft. So the piston drives the crankshaft, and the crankshaft drives the crank. So, and the cylinder over here, as you can see, my cylinder has got some ribs. These ribs are used for cooling so that the cylinder itself doesn't melt away, or the piston. And the piston moves up and down. Well, over here, these are some more important items. Here we've got the spark plug. And in a Otto cycle there is a spark plug, so in a spark ignition cycle. In a diesel cycle there's no spark plug. Over here we've got the inlet valve or intake valve. And the idea is that a mixture of air and fuel flows in when the intake valve is opened, and the area on top of the piston, so above the piston, will fill with this mixture of air and fuel. And the spark plug will give a spark, the mixture will combust, which increases pressure, which causes a increase of pressure, which will get the piston to move down. And when this has happened, there are some burning gases, exhaust gases, and they're going out through this gate, the exhaust valve. So, okay, so this is basically these are the technical items of my Otto cycle, of my gasoline engine. And now I'm going to discuss some important items that are used and that you need to be aware of. So over here, let's choose another color, and try to choose orange. Over here we have the lowest point the piston will move to, and that's called the BDC, and that's the bottom dead center. And the piston can't move any further than the bottom dead center. On top we've got the TDC, which is the top dead center. Top dead center. And the piston won't move any higher than the top dead center. And I'm not sure, I hope you can see it over there. But over here you can see that when moving from the bottom to the top, you can see that it doesn't touch the top of the cylinder, but there's some room in between, and that room is actually used for combustion. And after that, it's pushed down again. So it remains for, well, a split second. It will remain at this top dead center, and at the bottom as well. It will remain on the bottom dead center as well. Since the cylinder is of course cylindric, so we're not talking about the lengths, but we're talking about volumes. And there's one important length that you need to keep in mind. So that's the diameter of the cylinder, and that's called the bore. So, and we have some volumes that needs to be discussed. The volume above the top dead center has a name, and that's called the clearance volume. So that's the clearance between the piston and, for instance, a spark plug. And then we have this volume. It has a name as well. That's called the swept volume. Swept volume. And the swept volume is the volume that's refreshed in each stroke. And I'll explain you in a minute why, what I mean with refreshing. Okay. So what's the difference between a 4-stroke and a 2-stroke engine? Well, the 4-stroke engine has an intake valve for air and fuel and an exhaust valve. The 2-stroke engine doesn't have a valve, but has a gate. And usually in a 2-stroke engine, this volume is filled with fuel and air, and it will flow through this gate into the cylinder. So this is the intake gate. So when the piston goes down, a certain slightly lower pressure will be created, and fuel and air will be sucked into the cylinder head. And meanwhile, exhaust gases will flow out, and this is the exhaust gate. So there's no valve. These valves need to be locked and closed and opened mechanically, and these are just locked and opened naturally by this piston moving over here. Okay. Okay, I think these are the most important definitions we needed to discuss. Now I'm going into the working principle, which is probably more important than the layout which we just discussed. And the Otto cycle, actually the real cycle, so the gasoline engine cycle, which is over here, I'm going to write down here. This is the real cycle. I'm going to discuss the real cycle first and then go to an ideal cycle. So in the real cycle, the first stage I'm going to discuss is the compression stage. Compression. In this stage, the piston, so this is the piston, moves up this direction. And while this is done, the inlet valve and exhaust valve are both locked. So these ports, no fuel or air or whatever can move through. So it's locked. And of course, if I press this piston up, the fuel and air will be compressed. So so like this, moves up, everything will be compressed. And as soon as I'm in the top dead center, or slightly before the top dead center, the spark plug, there will be an electric current through the spark plug, and the spark plug will give a spark. And what happens then is ignition and expansion. Ignition, expansion. And actually, this is called the power stroke. So in this stroke, everything is ignited and well, a sudden push downward is given. And that's actually what we need, because we want to transfer some power. So I'm going to draw it over here. We have the spark plug giving a spark like this. And still all these valves are locked. So nothing flowing out. So there's only one way our piston can go, and that's the way down. And in this cycle, power is generated. So after that, the well, since it's of course attached to the crank, it will move up again, and we have a flywheel on the other side. This is a flywheel which will keep it going. So it will move up again, and while moving up, the exhaust gate will open like this. So, but the inlet valve will still be closed, and it's moving up. So now all air, all exhaust gases will flow out of my system, and this is called the exhaust stroke. Exhaust. So at that phase, all exhaust gases, all fumes are driven out, and when going back, slightly under pressure is created over here, and meanwhile the inlet port opens, and here the exhaust port is locked again, so no air can flow out, and that will look like this, with the piston moving down. So, and this is called the intake stroke. And of course, after this, the piston will move up again, and the whole cycle will start over and over. So this is the real gasoline or spark ignition cycle. Okay, since this cycle is really hard to describe thermodynamically, we want to idealize the cycle. And this can actually be done by using the air standard cycle. So it's an air standard cycle. And to describe this cycle, we need to do a couple of assumptions. So there is no difference in kinetic energy and potential energy. Actually, two processes are completely isentropic. Two processes are completely isochoric, so constant volume. Well, we're going to cheat a little, because sometimes we're going to assume that the whole system is adiabatic and perfectly isolated, and sometimes in some other well, comparable to the strokes here, we're going to assume that actually heat can flow in or out of the cycle. So let me show you. In the first stage, which is called isentropic compression, the cylinder is assumed to be perfectly isolated. So like this. No heat or mass or whatever can flow in or out. And during this cycle, compression takes place. So what will happen? The piston will move from position 1 to position 2. And this is called the isentropic compression. After this, so this happens in an isentropic fashion, so no increase or decrease of entropy. After this, so when we're at the almost at the top, dead center, so to speak, we'll have a heat flowing in, Q in. And in this stage, we actually assume, green, that the air heats up. So it's no combustion and expansion, but the air is just heating up, because we're talking about an ideal air situation. So and this happens at a constant volume. So the piston doesn't move. So this is called isochoric heat addition. And after that, of course, we're going to expand. And this happens again in an isentropic fashion. And again, the cylinder is isolated. So like this. And using green again. The cylinder will be moving from here, where it was, to here. So from 3 to 4. This is called isentropic expansion. And in the next stage, the piston will remain at the same position and heat is rejected. So over here we have heat going out. And this is stage 4 to 1. And we call this isochoric heat rejection. So actually this is how we would like to describe, how we do describe the Otto cycle as an ideal cycle, and to make some thermodynamic analysis of this spark ignition cycle. And of course, since we're engineers, we would like to see this schematically in a diagram. So I'm going to make the TS and PV diagrams, starting with the PV diagram over here. Pressure, volume, volume, pressure, and the TS diagram over there. It will help us to understand these principles a little better. So I'm going to start at point 1. And point 1 has actually the highest volume and the lowest pressure. So we're going to start over here. And after point 1, we'll go to point 2 and we'll do some compression. And we'll be isentropic. So this will look like this. So pressure gonna increase from 1 till 2. And from 2 till 3, I'm going to add heat. So the pressure will increase, but since it's isochoric, volume will remain the same. So this is what's gonna happen. So from point 3 to point 4, we're going to expand again. So we're going over here. It will look like this. 3 till 4. And from 4 till point 1, we're going to do the heat rejection. It will be isochoric, so the pressure, the volume will remain constant. So it will look like this. And this process can only happen in one way. So it will happen like this. Well, we're going to do the same for the TS diagram. Starting again with let's start with point 1 till point 2. We have the isentropic compression. So, and entropy will be lowest here, since temperature is lowest and pressure is lowest over there. So let's start over here. And it will be isentropic. So temperature will increase because of this compression. And the entropy will remain constant. So it will look like this. So you've got 1, there we've got 2. From 2 to 3, it will be isochoric, and we'll add heat, so temperature will increase. So it will look like this. Point 3, and from point 3 to point 4, we have this isentropic expansion. So point 4. From point 4 to point 1, we'll get rid of our heat rejection. It happened in an isochoric manner, so entropy will change. So it will look like this. And the direction of the cycle will be this direction. Based on this cycle, we can calculate the amount of heat and work. And from calculating this area under the PV diagram, we can calculate work out using this area. We can calculate the amount of work we need to put in, and something similar can be done for in the TS diagram. So this area over here will actually correspond to the Q in, and the area over here, let's choose another color, this will actually correspond to the Q out. So if you can calculate the integral, we know what Q out, Q in, work will be. Okay, since calculating an integral of these lines will be really complicated, we're going to dive into a little easier methods to calculate the work, the heat input and the performance of these cycles. Right now I'm going to derive the equations for the net work and efficiency of this Otto cycle, this ideal Otto cycle. And I'm going to start with calculating the work output and work input. And this will lead me to the net work. And these are the assumptions I need to do. Some processes are isentropic, and I will need these relations later on. And you can find them actually in paragraph 7.9 of the book. And I need the assumption from one of the first lectures about closed systems and energy balance, neglecting potential and kinetic energy, so changes in kinetic and potential energy, and I need to know what my difference in internal energy is. And so I'm going to start now. And the first thing I would like to do is calculate the work out. And that's actually equal to, well, looking to my idealized Otto cycle, this stroke is actually the stroke in which the work is done, isentropic expansion, so like here in the expansion process. So when the piston moves down, that's when the work is done. So my work out is equal to the work done from stage 3 to stage 4. And well, since in this stage the system is isolated, so no heat can flow in or out, you can assume that the heat flow is 0, so Q3, 4 will be 0. So from this we know that this is entirely equal to U, delta U, so the change in internal energy from stage 3 to stage 4, and that's equal to CV stage 3 minus stage 4. So for the work input, we know that the work input that happens during this process, going from 1 to 2, so that's equal to work 1, 2. Since over there is no heat exchange isn't possible, so it's perfectly isolated again, we know that this is equal to delta U 1, 2, gives me CV T2 minus T1. Check whether I did it correctly. Yes. So now we know that my net work will be equal to minus work in, and that's equal to CV T3 minus T4 minus T2 minus T1. Okay, so that's a net work, and when we would like to calculate the efficiency, we want to know the amount of energy we have to put into the system. So, and that will be the Q in, the heat energy we add to the system. So Q in, that's actually equal to Q1, Q2 till 3. So let's have a look, Q2 till 3, so that will be equal to delta U, because in our idealized system we know that no work is done during this process, since the volume from 2 till 3 is constant, so PDV doesn't mean anything in this case, so we know that CV will be equal to T3 minus T2. Okay. That's very convenient, I think, because now we want to calculate the efficiency. That's always very nice to know. So let's calculate the efficiency. The efficiency is equal to work net over Q in. And that's actually equal to CV T3 minus T4 minus T2 minus T1. And we have to divide all this by CV T3 minus T2. And this can be written a lot easier. And actually from this, one of the most important parameters in designing spark ignition cycles can be derived. And first you need to note that T3 and T4 are here as well. And that will lead you to is 1 minus T4 minus T1 over T3 minus T2. Okay? And using these relations of the isentropic process, I can rewrite this again. From this relation of the efficiency of the Otto cycle, and combine this with the relation for the isentropic processes. Since we know something more about the cycle, we can combine this into a very useful equation for the Otto cycle. Let's first check our isentropic processes, what happens in the isentropic processes. And there are actually two, going from 1 till 2 and from 4 till 3. So, and I'm going to use this equation that's underlined, and first going to check my process from 1 till 2. So T1 V1 k to the power minus V1 to the power k minus 1 is equal to T2 V2, and something similar is true for T3 V3 k to the power minus 1. No, I'm saying it wrong. It's V3 to the power k minus 1, and we have T4 V4 to the power k minus 1. And if you rearrange this, it will lead us to an equation for relating T1, T2, T3 and T4. We know that we have isochoric processes as well, and these isochoric processes are over here from 2 till 3 and 4 till 1. And actually from these processes we can say that V3 will be equal to V2, and we know that V4 will be equal to V1, as you can see over here. Okay, so this can all be combined. So from this we can say that T1 over T2 will be equal to V2 over V1 to the power k minus 1. So that follows from this part. So let's write it this way. Well, then from this part it follows that V2 is actually equal to V3 and V1 is equal to V4, and since this is power over here of k minus 1, that should be here as well, and that's equal to T4 over T3. So this is how all these processes relate into this equation, and we can rewrite this over here to is equal to 1 minus T4 over T3. You can check that for yourself, and this, and I'm going to continue over here, this will all be equal to 1 minus V3 over V4 to the power k minus 1, and this is actually equal to 1 minus 1 over r to the power k minus 1. And this r is a really interesting parameter. This r is the compression ratio, and this compression ratio is defined as V max, so at the bottom dead center over V min. So at the top dead center, the minimum volume over the maximum volume, and this is called the compression ratio, and this determines the performance of your Otto cycle. So the real Otto cycle, I'm going to show you a PV diagram, so pressure, volume, volume and pressure. And I'm going to start, well, easiest is to start at the, I'm going to start at the exhaust pressure, and that's about here. And exhaust, the intake and the exhaust stroke, they take place at approximately atmospheric pressure, and when in the exhaust stage we're going from a very high volume to a low volume because we want to remove all exhaust gases, and it happens as a slight overpressure since this valve is open, but so that looks a bit like this. Going over here, then we're coming to the, so this is the exhaust stroke, exhaust. After that we're going to the intake stroke. So then a slight vacuum, slight under pressure is the intake. And from the intake stroke we're really going to increase pressure. Both valves will be locked and we're going to push the cylinder, the piston upwards, and it will look like this. We're increasing pressure, increasing volume, and at a certain point, that's about here, we'll have ignition. And let me write down here, over here, we've got the bottom dead center, and over here we've got the top dead center. And slightly before the top dead center, ignition takes place. So not at the top dead center, slightly before. And then I'm going to increase pressure. Pressure will be rapidly increased to a certain point, then we'll move down again. There we start going down. Going down. And just before the bottom dead center, the exhaust valve opens. Exhaust valve opens. So from there, exhaust valves, fumes are going to be removed and pressure is going to decrease. So over here we have ignition. So this is compression, the compression stroke. Just use another color. Another color. Here we have compression. And here we have expansion. So this is what it looks like in reality. And in a 4-stroke engine, because in a 2-stroke engine this phase will be skipped. In a 4-stroke engine, and these are usually modeled in an ideal cycle as well. But since the volume in an ideal cycle and pressure during the exhaust and intake process will remain the same, the integral will be 0. So this is usually omitted in this analysis as well. So this is what it would look like in reality and what you can actually use to do your finite element analysis of any engine. I wish you good luck with the next part of this lecture, the diesel cycle. And I hope this will help, this lecture, this video will help you a lot to study the spark ignition cycles. Good luck.
Okay, for the next class, what can we look forward to? Well, we can look forward to talking about diesel engines, including turbochargers, something that you will see in the famous turbo TDI engines made by the Volkswagen consortium. This is the well-known slide with the many important formulas, and I must admit that when I prepare the slides and do some back of the envelope math, I often open this slide and look up the formula that I need. Hopefully it's just as useful for you as it is for me. Of course, many thanks again to Genie for letting us use her slides. And the famous final slide that hopefully helps you in storing things even more firmly in your memory I'd like you to look back at this class and think about the main takeaway messages. And I would also like to ask you if there were any things, any concepts that you found difficult to understand. Because if so, you might want to go back to them again and see if you can understand them by looking at it for a second time, or just join us in the Canvas meeting and ask, because that's what these Canvas meetings are also for. Okay, see you in class. Bye.